Welcome back. We are going to wrap up day 2 with uncertainty in measurement and sig figs. All right, so when we go back to chemistry and we're going to count and measure, we want to know, measuring is different than counting. Always has been, always will be. So when you count, some of you guys are related, listen to this, if you're related to the military or any teams or whatever, like if you're in the military, how many people do you have with you? You need to know that very accurately. You have 8 of you, right? You and 7 others, okay? Well, how many are now here? 5. Ooh, that's a problem. Like, well, I just don't know. That doesn't work, right? If you have $17 in your wallet for some reason, you know you have $17. If you have 2 pencils, you have 2 pencils. Easy counting. Measuring's different, right? Measurement is different. And those, great example, if you've done any type of flooring, you're gonna know that measuring is different. And what the other thing is, different even tape measures can give you different answers, right? Some of you already had, you got voluntold by dad or mom, hey, you're helping me with the tile or the floor or whatever. Or how long does this place need to be? And you measure it and they measure it and the tape measures are actually off a little bit. So there's uncertainty in measuring. And that uncertainty comes into, your device and how precise, how well your device measures, all right? Okay, and when we talk about this, we'll talk about accuracy and precision in the end here, but measuring always has some uncertainty, okay? There's always some uncertainty in the measurement, right? That's not necessarily human error. It is down to the limited ability of the instrument. So if you think about taking a ruler, right? Again, we're by a military base. Gunsmithing. So gunsmithing, they use thousandths of an inch. They need to be precise by. Partial, less than a millimeter. They're okay with, right? They're down to below a millimeter precision, right? Where some people, like if you're doing rough carpentry, right, you can be off by well more than a millimeter and it's fine, okay? And so it just depends on what you're measuring and how you're measuring it. All right. Now, when you're measuring, you only include in your answer or your measurements justified sig figs. Okay. How precise did you measure? You have to that has to be like fully known. All right. Otherwise, you're lying to people. We don't want to do that. Okay. Here's your weight. All right. Whether you like the number or not, that's what we're talking about. I have a mass. I have a weight. All right. And my weight at 8 a.m. is different than at noon. That's different at 8 p.m. Okay. That doesn't mean the scale's way wrong. It fluctuates. And so there's going to be, I'm not going to give myself like to the microgram of a weight. That's just not right. We do it to we do a whole kilogram, right? You can do a whole pound or 2. You don't go to the point pounds like, oh, I lost 0.1 pounds today. That's not a significantly measured figure because your weight will fluctuate. All right. So we need to determine, if we look at a number, how many sig figs there are. All right. Now, if you look, if there's a decimal, right? If there's a decimal, we go left to right. Okay. Draw an arrow from left to right until we find the first non-zero digit. All right. So in the first one, all of them, 1, 2, 3, 4, all 5 sig figs. Right, all 5 of them are measured, all right? Because you see the decimal, the 0.1's not an accident. And maybe it's 8230.1 meters. Perfect. The next one, all right, has 4 sig figs. Now, the 0 between 2 numbers is always going to be significant, all right? These 2 are important, but they're not measured. These 2 are placeholders. Important. But they're not measured. Well, what do you mean? How are they not measured? Think about if you took a 5 milligram allergy pill, let's say, or whatever, 5 milligram baby aspirin or something. So it's 5.041 milligrams. You have nothing else on the scale. Does that make sense? There's nothing else on the balance or the scale, so you didn't measure anything, right? So there's no, but it's very important that you take 5 milligrams of baby aspirin, not 5 grams of aspirin, right? That's a big difference. Okay, so the placeholders are very important, but they're not measured. So we use the term significant figured. It would be better to use the term measured figures, if that makes sense, right? Because you didn't measure anything over the 5 milligrams. You have no number there. You can't use it, right? Okay, so that's what we mean by, they're placeholders. They're important, but they're not measured, okay? Again, this is not about, it's weird now, right? It's getting weird because we're so used to counting, and $2 plus $3 is $5. But 2 grams plus 3 grams is around 5 grams, but it's not always, all right? Okay, and that's what's weird. So if there is no decimal, we go the other way, all right? Which would be from right to left. And so we have, in this number, 1, 2, 3, 4, 5 sig figs. And 3 placeholders. Those placeholders, again, they're very important. These are placeholders again. This very important, right? Because that number, right, would be what? 55 million. $55 million, $41,000, let's say. That's very significant. Those 3 placeholders are very significant because if we took those numbers off, it would be $55,041. That's a huge, huge difference. All right, so the placeholders are very important, but they're not measured. All right, so let's try these. Go ahead, if you need to pause it and you want to try it yourself, feel free. So you can pause it now. If not, let's dive in and go through it. So for the first one, 0.00105, right? There are 3 sig figs. 10.0010, this number, that is significant. So it's 2, 4, 6. This is significant. Right, that is significant. It's a 0 after the decimal, right? In fact, your calculator would not show you that 0. You have to add that 0. Since you have to add that 0, it's measured, it's significant, right? It's measured. 0.08206, you have 4 sig figs. All right. 1,000, you have 1 sig fig. Now, that is ambiguous, all right? Ambiguous. So when we talk about numbers, sometimes even counted numbers, like the population of your town, could be ridiculously small. 425, okay? Number of people in your high school, right? Or your elementary school, middle school, whatever it is, right? Your graduating class. But if you live in a bigger, like I'm recording this in Jacksonville, North Carolina, there's hundreds of thousands of people in here. And the problem is there's people moving in today and moving out today, right? And we're a military community, so we have people moving in and out every day, it seems like. And people are being born in this area. And people also, right, pass away in this area, right? And so we have a constant number of people going and coming, right? It's very hard to get an accurate count. So it's ambiguous, so you don't use it. So it's probably not just 1 sig fig, 1,000. However, you use scientific notation to avoid that ambiguity. So like 1.0 times 10 to the second. So when we talk about scientific notation, this number as written would be 1.0. So we wouldn't even put the decimal point down. It should be 1 times 10 to the third. If I had 1.0 times 10 to the third, that's 2 sig figs. 1.00 times 10 to the third, that's 3 sig figs, because everything written in scientific notation is significant. All right, so that's how you tell how many are there. Next, what do we do when we have to manipulate these numbers? So there's 2 operations, addition and multiplication. So addition and subtraction, multiplication and division. All right, and it's because of the error in measurement. And we say error, it's just because there's the uncertainty in measurement. All right, it's not that you did something wrong. I mean, we could measure wrong. We can measure incorrectly. All right, but if you measure to the best of the tool's ability, there's still going to be what quote unquote measuring error or measuring inaccuracies. And so, how do we deal with that when we add and subtract? We go to the right as far as possible. So if I was going to add this number up, right, I have 8,335.7031. All right. I go here and I can go to the 10th spot. Is it? That's all I can go to. I have no data out there. There's no data, so I can't add that. Like I have nothing to go on there because that could be 301.29, 301.20. That's a huge. We don't know where it is, and so that's where I have. I can't assume anything. So now what I do is I look at this 3, and since that's a 3, we're going to round down, so this becomes 1307.5. That's it. All right. So when we add and subtract, we go to the right as far as possible. Multiplication and division is different. Multiplication and division, because you're taking your uncertainty in the measurement and you're compounding it. All right. You use the least number of sig figs. So this is where students like, oh gosh, I don't like this, and it feels like you lose data sometimes. Feels like you lose numbers, but you're not losing anything because you didn't have it there to begin with, if that makes sense, right? Okay, if you don't have it there to begin with, you didn't lose it, all right? Okay, so if I take 12.1 and divide that by 10, I get 1.21. 3 sig figs, 1 sig fig. So 1 sig fig is what limits me. So that means my answer can only have 1 sig fig, so I get 1. So that looks like I lost information, but my 10 was not measured very precisely or very accurately or both. And so that's divided by just 10. Now, if I divided by 10.0, I could keep all 3 sig figs because they'd all be significant or measured. But right now, it's not, so I can only keep the 1. And a lot of people don't like that, but that's the way it is. Now, when we talk with this, there's things called exact numbers. And exact numbers have no uncertainty, all right? So if I have 7 quarters, there's no, could it be 8? No. How many people live in your house? That probably should be an exact number, right? How many people do you have with your car with you at any time? Exact number, all right? How many rings are you wearing? Exact number, right? You guys get it. Define quantities, like 100 centimeters in a meter. Also, 2.54 centimeters is 1 inch. That's by definition. That's an exact number. So those will not limit you. Also, these integers here, right? These integers right here, 4 and 3, they do not limit you in the calculations. Like, so if you're trying to take the volume of a sphere, that's what this is. This equation is volume of a sphere. If you take the volume of a sphere, and you're like, oh, I have a 4 and a 3, so I get 1 sig fig. No, they're exact numbers. They do not limit you, right? In fact, most of the time when I go from English to metric conversions, which is what's next up, I use the 2.54 because it's exact, right? It doesn't limit my sig figs. Now, most of the time for us, it doesn't matter, but I like that, all right? So those are the exact numbers. Last topic of the video, accuracy and precision. All right, so if I'm going to have target with, I'm going to do that, with the bullseye. All right, there's my bullseye. Is it in the middle? No, not quite. Maybe I can move it. There we go. Perfect, close enough. All right, let's talk about accuracy. Is agreement of the value with the true value. So obviously, the number one goal we would want is we would want to have there, and there, right? That would be ideal. So that would be both accurate and precise. So the green right, is accurate. The X's are both accurate and precise. All right. What if I had there, 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 and there? What would that be? All right. They're very tight, right? So the dots here are precise, but they're not accurate. And then, what if I had that? Those, the average, right? Because if you took the average here, the average is right in the bullseye. So these are accurate, but not precise. Obviously, green would be the best, right? Accurate and precise. The purple would be our second best, because if you're doing the purple, chances are you have a systematic error. We can get you to where you need to go, right? The blue is kind of like a blind squirrel finding a nut. You just happen to, unless you did that on purpose, no way, all right? Now, usually as you try to increase precision, your accuracy goes down. What do I mean? Well, again, we're in a military town, so we used to, now there's no more, but we used to have a scout sniper school here at the military Marine base, all right? And then, of course, we have an air station. They have, let's say they have bombs. If there is a parking lot with a bad guy in it, in the parking lot, all right? The scout sniper, right? The scout sniper is a way more precise weapon than a 500-pound bomb, right? Now, how close does the 500-pound bomb need to be accurate and make the kill on the bad guy? Well, it doesn't have to be that close, right? It can be off by several meters, and that's probably going to be fine, right? However, the scout sniper, how off could he be in his shot? Well, if he's off by a meter, he completely missed, not even close, right? So usually when we try to get more and more precise, accuracy kind of it gets more and more fuzzy sometimes, just because of when we're talking about measuring. A lot of times in chemistry, we're measuring very small amounts of very small items, and so sometimes that accuracy and precision, right? That we try to get really, really precise. Sometimes our accuracy, bubble gets bigger. All right. So that's accuracy, that's precision. Hopefully that that makes sense. And that's going to end day 2. All right. If there's any questions, let me know. Otherwise, we'll see you next time, guys. Take care.